Good evening. I hope you managed to see Austin's comet. This rather splendid photograph of it was taken by Ron Arbour, and it shows the comet well. There's the head, and you can see quite a long tail. Of course, the comet never became bright, but it was visible with the naked eye. I'm afraid we've seen the last of it now, because it's faded down below naked eye visibility, and it's got a very long period, of a good many centuries, so I'm afraid we won't be seeing it again. But it was the brightest comet for some time. And incidentally, people have been writing to me about Halley's Comet, which is on its way back and will come to perihelion again in early 1986. Well, searches for it are going on already, notably in Australia with the UK Schmidt at Siding Spring, but they've not been successful so far because the comet is still very faint indeed. I think it will probably be rediscovered either this year or next, but it won't become a naked eye object until about November 1985, and I'm afraid it's not going to be really spectacular even then. But of course, it is an important comet, and don't forget, several rocket probes are due to be sent to it, so we'll have a great deal more to say about Halley's Comet nearer the time. I'm afraid that the autumn skies are not rich in planets. There are no bright planets on view, but there are plenty of stars. And of course, we still have what I call the summer triangle, made up of the brilliant blue Vega in Lyra, Deneb in Cygnus the Swan, or the Northern Cross if you like, and Altair in Aquila the Eagle. And Altair is easy to recognize because of the fainter stars of either side of it. The same applies to Antares in the Scorpion, but there's no danger of confusion because Altair is brighter and white and higher up, and Antares now has more or less gone down into the twilight anyway. But Vega, that brilliant blue star in the harp, is almost overhead during summer evenings. In winter evenings, it's the turn of Capella in the Charioteer to be overhead. And in fact, Vega and Capella are on opposite sides of the pole star and about the same distance from it. So when Vega is descending, as it is now, Capella is rising. But look at that little triangle of stars just by Capella, the three stars known as the Kids, Epsilon, Eta, and Zeta Aurigui. Now, Epsilon is that remarkable star to which we devoted a complete program a little while ago. Every 27 years, it fades down by about a magnitude as it is eclipsed by an invisible companion. And we don't really know what that companion is. It may be a disk of gas, it may be a curious kind of star. We don't really know. But certainly it does happen every 27 years, and the eclipse has just started. So if you look at the Kids now, you will find that Epsilon at the top of the triangle is just a bit fainter than Eta on the left-hand side, instead of being slightly brighter as it usually is. Well, this really is a most remarkable system, and since the eclipses only happen once in 27 years, astronomers all over the world are now paying very close attention to it. And by the end of the year, it will have gone down to about the 4th magnitude, though of course it's always clearly visible with the naked eye. Of the autumn constellations, I suppose the most celebrated is the flying horse, Pegasus, whose 4 main stars make up a prominent square now high in the south. Although I must admit that maps and charts very often tend to make the square look smaller and brighter than it really is. The stars are not particularly bright, but they do make up a distinctive pattern, and you can't miss them. And well below the square is Fomalhaut, in the otherwise unremarkable constellation of the Southern Fish, which is actually the southernmost of the bright stars ever visible from England, and from North Scotland it hardly rises at all. Now, leading away from Pegasus is the line of stars making up the constellation of Andromeda. And for some reason that I've never been able to fathom, one of the stars in the square, Alpheratz, has been given a free transfer into Andromeda, which doesn't seem very sensible to me because it so obviously makes up part of the square pattern, but there it is. The end star of the line of Andromeda is called Almach, about as bright as the pole star, and telescopically a lovely binary with an orange primary and a bluish companion. But also in Andromeda, we have that very famous object, M31, the Great Galaxy, one of the nearest of the galaxies and the nearest really large system to our own. You can just about see it with the naked eye on a clear night, and binoculars show it well. Although some people looking at it telescopically do find it rather disappointing. Now, this picture was taken by Commander Hatfield, and that does give a very good impression of the Great Spiral as you see it with a small telescope. But when it's photographed with a large telescope, then the real form comes out. And it is, in fact, a spiral, although it's not face on to us, unfortunately, and the full beauty is lost. But there it is, a spiral galaxy, rather more than 2 million light years away. Now, spirals are very common among galaxies, and some of them are, of course, face on, such as the famous Whirlpool in the little constellation of the hunting dogs, and that is beautifully displayed, although I'm afraid you won't see it with the naked eye. You can see there the arms are very well developed. But in other spirals, the arms are tightly wound. Look at this one in the constellation of the Whale. You can hardly see the arms at all, and the nucleus is bright. Others are loose, and there's a very good example of a loose spiral in the little constellation of Triangulum, the triangle, again quite close to Andromeda. This is Messier 33. You won't see it with the naked eye. You might pick it up with binoculars, but it's by no means conspicuous. When photographed with a large telescope, the spiral arms are there all right, but they are by no means well defined, so the spiral is a very loose one. And from that, you can see that spirals come in all kinds. And our own particular galaxy in which we live is itself a spiral. It's a flattened system, and when we look along the main plane of the galaxy, we see many stars in almost the same line of sight, and that, of course, produces the famous Milky Way appearance. But if seen from above, or below, so to speak, our galaxy, too, would give the impression of being a spiral. And the Sun, with the Earth and the other planets, lies quite close to the edge of one of the spiral arms. And seen from the edge, of course, the galaxy would appear like this. And we do see many spirals almost edge-on. But the spiral arms are important, and they're also very mysterious. There's a great deal about spiral galaxies we don't understand. At this stage, I'm delighted to welcome back once again Dr. John Beckman of Queen Mary College. Delighted to see you, John. Now, in our own galaxy, the Sun, as we know, lies near the edge of a spiral arm, and we are something like 30 million light years from the center of the galaxy. And the galaxy is going round, it's revolving, and the Sun takes something like 225 million years to go once round. And that means it's probably been round the center of the galaxy about 10 times since the universe came into existence. And you would have thought, under those circumstances, that the spiral arms would have wound up and disappeared.
You would have thought so, because the center of a galaxy, our galaxy and others, goes round more quickly than the outside. I think the best way of thinking about that is to imagine the solar system to begin with. Mercury going very quickly around the Sun, it takes about 88 days. The Earth, of course, 1 year. Picking out Jupiter, 12 years. And going out to Pluto, 248 years. The outer ones are slower. Now, imagine a string joining the planets. As the planets go around at their different speeds, the string would take the form of something like a spiral arm.
Yes.
But because the inner ones are zipping around so quickly, the spiral arm would rapidly coil up on itself, and very, very soon wouldn't be a spiral arm at all. It would just be a very tight coil and wouldn't look like a galaxy at all. Now, the same sort of thing is true of the galaxies. The principles are the same. The principles of the motion is the same. Of course, the galaxies aren't exactly like the solar system. There isn't one mass at the center. But the idea that the center moves more quickly than the outside is still very similar. And in about 10% of the lifetime of our galaxy or any other spiral galaxy, the arms would wind in on themselves and effectively disappear as arms.
Quite so. So there shouldn't be any spiral arms at all. But there are. Why?
Well, that's the paradox. There shouldn't be spiral arms, but there are. And that means that as the arms really do wind up and disappear, something must make sure that they are replenished.
And how can that happen?
I think before really going into the details of how it does happen, the best thing would be to take a look at different types of galaxies and the differences between them to show how spirals differ from the others. Now, there are normal galaxies and there are active galaxies. Well, let's forget the active galaxies. Yes. They're very exciting, the quasars, BL-like objects and so on. Radio galaxies, they're relatively few. Yeah. Let's concentrate on the normal galaxies. Now, of the normal galaxies, there are three broad classifications. There are ellipticals, irregulars, and spirals. The ellipticals are, as their name implies, of elliptical shape. But perhaps more important for this, they have turned all of their original gas into stars. There's no gas left virtually in them, so that the brightest of the elliptical galaxies are the brightest of all galaxies because all the material is in stars shining. Now, the irregular galaxies are partly stars and partly the original gas with a bit of dust, and they take an irregular shape because they're not rotating very quickly. The spiral galaxies, the third sort, have still a lot of gas, stars, but they are also rotating. So there are the differences. Now, it used to be thought that these formed a kind of evolutionary sequence, but nowadays that's not the general view.
Yeah.
The view is that the differences come from differences of formation. And as we don't yet have the ability to observe forming galaxies, we can't say too much about that. But what we can say a lot about is the actual morphology of the galaxies, the shapes. Here are some characteristic ellipticals and irregulars put together to show the differences. You can see that the ellipticals go all the way from virtually globular galaxies to very elongated ellipticals, and the irregular ones are raggedy at the edges and have a rather nondescript appearance. Now, the spirals, on the other hand, are what everybody actually thinks of as galaxies, really. That's the image that first comes to mind. There are two main types. There are the ordinary spirals, which may be tightly wound or loosely wound, as you said before, and there are the barred spirals, which have a rather crisp, sharp bar in the middle of them. The next picture is a schematic showing how the different sorts of galaxies are classified according to whether they are more or less tightly wound in the case of spirals, and in the case of barred spirals too, and in the ellipticals they are classified according to how globular or how elongated they are. Some of the spiral galaxies are among the most famous galaxies that we know. Here again is the Andromeda galaxy. It really is very beautiful, and the spiral arms are rather well seen, even though it isn't face-on. You can see them as rather faint, but definitely spiraling outwards from the central globular bulge. Now, some galaxies are edge-on to us. They are the same sort of galaxies, but they are looked at from a different angle, like this one, NGC 253. Here you can see the spiral arms, but not too well as spirals. You can see the dust and you can see the gas that makes up the arms set glowing by the stars in them. And if you really want to have a full display, you can have one by finding a galaxy that's face-on. And in this case, this is M74 with very, very well picked out and clear spiral arms. And then here we have a barred spiral, again with a very vivid and beautifully expressed bar, with the arms jerking quickly away from the bar. Now, there's a lot of dynamics involved, which I'm not going to go into. I think another thing, I shouldn't leave the impression that that these galaxies occur singly, that they occur isolated. They're in clusters. Nearly all galaxies are in clusters, some big, some small. This is the Virgo cluster. It's a fairly nearby cluster. It's a very well-studied one, and it contains both ellipticals and spirals of all kinds.
Well, the spiral arms must be some kind of a wave motion, surely.
Yes, it almost seems self-evident that they are. And as I said, what differentiates spirals is the fact that they spin and that they have gas and dust, particularly the gas. And as the stars spin, what happens is that the gas is made to go into a kind of a wave pattern, a so-called spiral density wave pattern. The gas takes ribbed form. It's a bit like the waves on a pond. It's not a very good analogy, but at least the waves on a pond have the characteristic that they don't move. They appear to move while the pond as a whole stays still. Now, the same sort of thing is going on in a galaxy, but spinning, not moving outwards. There are these density waves that are in the gas, but they don't spin round at the same speed as the rest of the galaxy. And it's in those waves that the stars that form the spiral arms are formed, because where the waves are denser, there stars can form. And what happens is that the stars form. Once the stars have formed, they are spiral and they begin to wind up again, just as we saw earlier.
Well, then why don't the spiral arms vanish?
Well, here you have to imagine that we are seeing the spiral arms by means of the brightest stars in them, the most luminous, the most massive, brilliant stars. Now, stars like that are very greedy. They gobble their way through their nuclear fuel so quickly that in the time scale of a galaxy, they go out like a light. They're almost like lighthouses, flashing on and off. And so that after about 1 million to 10 million years, which is very short, they've gone. The smaller stars stay there, but they're not so easily seen. And so what happens is that these spiral arms flash on, flash off again, but by that time, the density wave has already moved on a little bit. Not very far, but it's moved on a little bit, and so new stars can form in the new density wave position, and a new spiral arm is formed.
So no individual spiral arm is a permanent feature, but new spiral arms are forming all the time out of the gas.
That's exactly so. The There are two reasons why this happened. One is what I've already more or less alluded to, that is that the places where the gas is most dense are the places where stars are most likely to form anyway. But also, the dying throes of the previous arm, the explosions of the stars which are dying, the supernova explosions, send a shock wave into the next bit of gas and trigger off the next piece of star formation. Now, I think I ought to be clear that all of what I've been telling you is hypothetical. It's theory mixed in with experiment. We need a lot more observations, and these, of course, are being done. It takes radio astronomers, it takes investigating the gas clouds by millimeter astronomy, the dust and the stars by infrared, and finally optical astronomy to get a complete picture.
Let us not neglect photography. Colour photographs are beautiful. They're also highly instructive.
Last year, some astronomers from Queen Mary College took a set of colour photographs of some southern spiral galaxies. They took these photographs through colour filters in the visual, infrared and red in preparation for measurements of the gas in galaxies, carbon monoxide, which is in fact a different kind of measurement.
Yes, quite.
And Steve Adams, the photographer in the physics department at Queen Mary College, has put these photographs together in a rather attractive and good-looking way in the form of colour transparencies, which can be overlaid to give a very, very good impression of the galaxies themselves. We can see here the visual plate of the galaxy put into blue. The colour is false, but it does give the impression. And then the red, and then the infrared masked down, and the total effect is to show very clearly the spiral arms, as you can see, and you can also see what are called H2 regions. These are the areas of gas, the volumes of gas lit up by the very, very hot luminous stars inside them. It gives a particularly vivid impression of the galaxy, but of course we can learn from it where the young, old and stars are, and where the gas is as well, and where the dust is. Now, we can learn a great deal from this, but there's a great deal more unlearned. You couldn't tell by looking at a picture of that kind, for example, where all the invisible mass lies outside the visible arms. You couldn't tell, although it looks as if it's swirling, you can't tell the speed, and you can't measure the mass of a galaxy by looking at it. You can, however, measure it in a variety of ways. And the concatenation of different techniques which goes into the description of a spiral galaxy, the radio, the millimeter wave, the infrared and the visual, all leading to an enhanced understanding of these very difficult processes. But of course there are many questions left unanswered.
Well, certainly we know a great deal more now than we did only a few years ago. John, thank you very much indeed. So remember, we live in one particular part of the universe. There are many other galaxies. And when we look at a well-displayed spiral galaxy, such as M83 in Hydra, the detail there is quite remarkable. And we are far yet from understanding it all, but we have made remarkable progress. And I think, you know, that when we're studying the universe as a whole, we really got to start by studying the evolution of the galaxies. And this is where the spirals come in so useful. Before I go, our new newsletter is ready, number 7. If you want it, as usual, send your stamped addressed envelope to this address. Newsletter number 7, The Sky at Night, BBC TV, London, W12 8QT. But I'm afraid we must insist on the stamped addressed envelope. It's the only way we can work it. But there's certainly plenty to see in the sky, even though at the moment there are no bright planets on view. So until next month, good night.